again, Courtney, thank you very much to be here with us, sharing a little bit of your knowledge, which is immense knowledge. So I'd like to introduce you. Dr. Courtney Young is a graduate from 3 premier institutions, obtaining his BS in Mineral Processing Engineering from Montana Tech, MS in Mining and Mineral Engineering from Virginia Tech, and his PhD in Metallurgical Engineering from the University of Utah. Definitely 3 major premier institutions. Curta returned to Montana Tech in 1993 as their first ever postdoc and became a professor 2 years later. As a faculty member, he served as department head from 1998 to 2009 and has named the Ascot Professor from 1996 to 2005 and Lewis S. Potter Distinguished Professor up to today from 2006. Dr. Young has advised the students' research so far for 120 undergraduates and 46 MS, masters, and PhD students, mostly with funding from the mining industry. Research topics have varied over the years in mineral processing and extractive metallurgy, including application thereof, recycling, and remediation. Courtney has been extremely active with SME as an author, officer, presenter, session organizer, and symposium chair. He has published, edited, and presented nearly 200 papers and books. And I'd like to add that I met Courtney Young in one of the SME conference in 2019 in Denver, Colorado. So again, Dr. Young, it's a pleasure and an honor to have you here. Okay. They're not physical anymore, unfortunately, but the digital show, it's all yours. Thank you so much.
All right, Andre, thank you very much. If I may say, Andre, on a first name basis, you know, and I gave this presentation back in the Phoenix meeting, February of 2019. It was nominated for a Henry Crum lecture, which surprised me. It was then picked by a panel. So it's a pleasure to be speaking to all of you. Now, the way I'm going to do this is I would like it to be interactive. So if you want to stop me and ask a question, feel free to do that. Because I want it to also be like it's a classroom lecture and open to questions. I don't know how to use this system all that well. I presume that there's a chat someplace. You raise your hand if you have a question. I would suggest just unmute yourself and ask. But I'll try to pay attention to the chat room. So you can see the title of my presentation there. And as soon as I get my cursor going, it was presented, like I said, at the SME meeting in Phoenix in February of 2020. And this was one of the MPD division meetings. It was a session called Flotation 2. I am with Montana Tech, as Louise knows. My co-authors are Simon Timbala. He was the PhD student on this project. Rick Leducer was the second postdoc. He is now a faculty member in mechanical engineering. And Dr. Doss was my first postdoc on this, but he's now a faculty in my department. Our co-author on this is Debbie Laney. She is a engineer, mineral processing engineer for Chevron Phillips Chemical Company. And as Andre noted, that my favorite thing to do is to work with industry as a faculty member. The outline of my talk is as you see here. I'll start off with some general comments, tell you what Orfom D8 is, show you its chemical structure, and then I'll go through the reviewing it as its mechanism and then go through some lab study and some plant trials. Then I'll throw up some conclusions and some acknowledgments at the end. So copper, as we all know, and you guys have a neighbor in Chile who's a very big producer of copper, Peru. I'm not sure how many copper mines are in Brazil, but I know you have a few. But copper, of course, is a base metal. It's got huge demand as of right now, and it's going to do nothing but get larger. So we're going to need more and more resources. Most copper comes from either leaching of copper oxides and hydroxides and silicate type minerals, but it also predominantly comes from the flotation of sulfide ores. Most of the time in that flotation process, it's about chalcopyrite. In sulfide ores, predominantly the chalcopyrite will be associated with pyrite, pyrrhotite, sphalerite, galena, and what we're most interested in for today's lecture is the molybdenite. Flotation of copper moly ores typically involves a rougher scavenger cleaner circuits, where the rougher scavenger float gives you what we call a bulk sulfide concentrate. That concentrate is then cleaned in another circuit where you upgrade the copper and the moly, typically following a regrind stage. This part of the flotation step involves a xanthate, typically isopropyl xanthate for the collector for copper, and diesel fuel is added as the collector for moly or the molybdenite. And molybdenite, of course, most of you know that it is naturally hydrophobic, so the diesel fuel just makes it that much more hydrophobic. This bulk sulfide concentrate is then brought over to the moly plant, where a rougher and 3 cleaner stages are used to upgrade the two and separate the copper from the moly, and you produce 2 products. In this case, you float the moly in the 4 stages, and you're depressing the copper in those 4 stages to produce your final concentrate. That in order to depress the copper, most people use NaSH, the sodium bisulfide, to depress the NaSH. You can use sodium sulfide, sodium cyanide, or NOx reagent to do that. There are problems with this. And so there's a tendency to go after these organics, which help overcome those problems. And those problems include safety issues with NaSH. It's hazardous, and boy, does it stink. I think most of you know that. Economic-wise, you use a lot of NaSH, high consumption, and of course, you have to keep on using it because it decomposes with oxygen, and the NaSH eventually becomes sulfite and sulfate. And of course, it loses its depression powers after that. Materials handling is not easy. You got transportation, very careful transportation costs because of these issues. Sample prep is a little bit of time in order to introduce it into the flotation cell. And of course, it takes high volumes. In the case of the organics, and particularly with Orfom D8, it is safer. It performs equally, if not better, than NaSH. It's easier to handle. It's better cost-wise. And certainly it's a future alternative, and people are really starting to look at that. And then, of course, if you address all these issues, it's always about mining sustainability. So what is disodium carboxymethylthiciotrithiocarbonate? This is its structure, and you can see the 3 thiol groups or sulfur groups. This is an anionic head group, so you need sodium to counter that anionic charge. There's a carbon there and a carbon there. And on this this carbon are 2 oxygens. So this is the carbonate group. Of course, it has a negative charge to it, and you need another sodium to counter that charge. So hence you've got disodium, carboxymethyl, and here's your carbonate group, and here's your trithiocarbonate. So pretty simple compound. We decided to try to model this electrostatic potential surface, and you can pretty much see that the sodium kind of resides right in the center of all of these sulfurs. And then you've got your methyl group in here where there's pretty much no charge. That's why it's white in there. And then this sodium kind of resides back and forth depending on how this bond resonates. This sodium can spend some time kind of resonating itself. So you see the electrostatic model is kind of interesting. What I want to do though is compare that structure to, in this case, ethyl xanthate. And if you look on this side of the molecule, there's really no difference with the exception that this oxygen replaces that sulfur. You still have a carbon group there, and instead of carbonate, you have a CH3 group here. So this molecule might respond very similar to xanthate on this side, but of course this molecule is charged on both ends, and this molecule is hydrophobic on this end and hydrophilic on this end. So we're not going to do anything fancy. We're going to take a look at some cyclic voltammetry, and we're just going to look at copper metal at pH 9.5, 9.4, and that pH, it comes from 0.05 molar sodium borate. Our scan rate here is 10 millivolts per second. And so we start here where reaction 1 is occurring, and we get hydrogen gas evolution. This is not a surprise. And then as you scan, you go through an area zone here where there is no current. Of course, this is where copper metal is stable until you reach about an EH of 0. And then you see this peak. And that peak is where you form copper 1 hydroxide. And then you get to a second peak in here where you start to see a little bit more current flowing. This is where you form copper 2 hydroxide. And then, of course, you get way out to 4 here, and that's oxygen evolution. Okay, no surprises. And then when you put xanthate in the system, and this is known in the literature, so we know this system extremely well. And I'm going to toggle back and forth between the two so you can see the differences. And quite clearly, the difference comes with this peak here and this peak here. So to identify those peaks, peak 5 is xanthate chemisorbing and giving up an electron. So that's peak 5. This is called xanthate chemisorption. The second peak, number 6 here, is where copper itself reacts with the xanthate, and it precipitates out copper xanthate and gives up an electron. So this is just known as surface precipitation. Everything else is the same. Now we're going to put D8 in the system. And remember, this is charged on both ends, so it's a double anion, divalent. And 1, you get your peaks back. You get your hydrogen evolution pack. You get a new peak here. And because we believe it's reacting through the sulfide, the thio group functionality on the D8, that we believe it follows what xanthate does. So this molecule chemisorbs and gives up an electron. And then the next peak, we see it kind of responding the same way as xanthate again, where you get surface precipitation, except it's not really surface precipitation. I'll explain in a second. And then the next peak, you get surface precipitation. 2 of these are forming with each copper. Okay, and in each case, an electron is being given up, and you're seeing these 3 peaks, which kind of mimics the xanthate. So we're pretty comfortable with what we're seeing. But the point is that these reactions occur in the presence of xanthate. Xanthate's on the surface. All right, so we should get our hydroxide peaks back, and we do. We see this peak here, and we sort of see a peak here. Ignore this guy. It was just an artifact. I think we had a lightning strike during this, and we saw a little spike in the voltammogram. Didn't ruin the study. It's just that it happened. And then, of course, as you continue to go, you start to see more current because of oxygen evolution. So xanthate is present, and yet D8 reactions are occurring, which tells you that D8 is masking what the xanthate does. Okay, so if it's electrochemically active, then maybe we can see something by X-ray photoelectron spectroscopy. So we're going to take a look at the copper 2p 3/2 peak, and this is just chalcopyrite. So you see a peak here at 933.4, somewhere in there, or 933, and then you see a second peak in here. Okay, and this peak is the one we're going to monitor. And we're going to compare that with chalcopyrite with Orfom D8 present. And here's the peak 1. It's the same position. So we don't care about that one. It's this guy that we're seeing a change in. And when we look at that without Orfom D8, that peak position is 934.8 electron volts. And it moves to 933.73 electron volts. The difference between those two is negative 1.07, and basically that's telling you that copper is being reduced from copper 2 over here when Orfom D8 is present to copper 1. So we have a reduction reaction that could account for the electrochemistry of the Orfom D8 itself. So let's look at the iron 2p, and we're going to see the same thing. In this case, we're going to look at peak 1 here, and you can see that moderately compares, it's a little bit less in height, but over here, all of a sudden it's greater in height. When we look at that peak position, it's 709.01 electron volts here. It's 710.65 over here. In this case, it's plus 1.64 electron volts difference, and that's telling you that the iron 2 is oxidizing to iron 3 in the presence of Orfom D8. So Orfom D8 is causing the copper to reduce and the iron to oxidize. And I'm going to skip this because it doesn't add to the story, and I don't need to really cover that. Okay, and I want to spend some time with you guys after this. So the faster I am on this talk, the better off we're going to be. Anyways, FTIR spectroscopy, we also used it, and chalcopyrite has a peak of around 1160.96, pure chalcopyrite. Pure Orfom D8, a carbon sulfur double bond is 1227.47 wave numbers. And then the carbon sulfur single bond is about 1011 wave numbers. Both of these bonds change their position to 1253.52 in comparison and 1022.1. So this shift is telling you that the Orfom D8 is reacting with the chalcopyrite through the sulfur functionalities, not through the carbonate functionalities. And then we tried to look for the xanthate that's already on the surface to see if it would desorb. So here's the xanthate peak at 447.41 with KEX. So this signal, this COC bond is coming from potassium methyl xanthate. We put Orfom D8 in that system. If it does not desorb, then this signal should remain the same. It's not a very good spectrum, but sure enough, you're seeing a peak at 447.41, telling you that the xanthate is still on the surface. So Orfom D8 does not desorb the xanthate to depress the chalcopyrite. So let's take a look at zeta potential. With Orfom D8, here's the chalcopyrite without Orfom D8. I should start there. And that's this plot that you see here. If you go above pH 10, then you start to get charge reversal. I'm mostly interested in here from pH 6 to 10, give or take. And then when you add xanthate, that's this plot, right? I hate these colors. That's this plot here. And for the most part in here, you're not seeing a lot of change. You do see a fair amount of change above pH 10. We're not interested in this. We're interested in here. And of course, where you're seeing the most change is right in here. This is fairly uncharged, really negative. It's telling you that the Orfom D8 is really on the surface. And because it's an anion, it's changing that zeta potential tremendously. In comparison, here's the moly without D8. That's this gray plot. Not a lot going on in there. It's hugging around 0. Pretty low numbers. Put Orfom D8 with the moly. You see a little bit of a change, but there's not a lot of change in there. So it's telling you that the moly really does not react with the Orfom D8, or the Orfom D8 does not really react with the moly. So the moly really doesn't change. The chalcopyrite really changes, particularly in this pH range from 7 till about 10. And that's where we're most interested. Absorption appears to be specific to chalcopyrite as a result. So the other thing that we did is we took a look at, can we try to measure an absorption density of Orfom D8 on chalcopyrite and on molybdenite? And what we're able to see here is that we get significant absorption on the chalcopyrite, but very little absorption on the moly. So if you're going to get depression action, it's going to happen with the chalcopyrite and not with the moly. So absorption again is specific for the chalcopyrite. It occurs through the sulfur functionalities. It involves chemisorption because we're seeing electron transfer. And it may be a bidentate or monodentate. We don't know. I'll talk about this in a second. It does not desorb the xanthate, which is different from sodium bisulfide, the NaSH. So, and that's because we just don't see xanthate detected in solution. So what we want to now do is then go on and start looking at some lab studies. But let's talk about this bidentate, monodentate stuff. So carboxylate protrudes into solution. So here's the Orfom D8. And here I'm showing it as a bidentate. Again, we don't know if this is the case or not, but this sulfur bonds with this copper, this sulfur bonds with that copper, and this is the Orfom D8 adsorbing onto the surface, chemisorbing onto that surface. It blocks the xanthate hydrophobicity. And here is a model of the ethyl xanthate adsorbing. In this case, just to show you the difference, this sulfur and this sulfur are bonding to the same copper, and that's a monodentate. Otherwise, they're almost the same length. This is a little bit taller than the xanthate. Everything is the same. hydrophobic forces do not reach very far into solution, where anionic or electrical forces will reach much further into solution. And this is why it can mask the hydrophobicity of the ethyl xanthate that's absorbed onto the chalcopyrite and depress it. So it induces hydrophilicity, and depending on the xanthate length, if I went to isopropyl xanthate, I included another carbon in here, we expect that we would also see depression still. But if we went to amyl xanthate, it probably wouldn't work very well, because then the xanthate molecule is too long. But that's some research that has yet to be done. Just by comparison, the NaSH and these other compounds, they desorb the xanthate from the surface by lowering the oxidation reduction potential. Okay, and once again, Orfom D8 does not cause desorption. Okay, and the natural hydrophobicity of moly is probably playing a role, and we're going to actually talk to that in a second. Okay, so the other thing that we did was we went into and decided to do some modeling by density function theory. I'm not very good at this, but from what I understand, you take the lowest unoccupied molecular orbital, and so all these orbitals that an electron can occupy are occupied. The next one that's up there is the lowest unoccupied. So we're going to take a look at that energy level. And then we're going to go to the HOMO, or the highest occupied molecular orbital, and that is this guy. And this difference in energy is what we're interested in. So this is plus 0.1 volt. This is minus 3 volts. And of course, the difference between this energy and this energy is 3.1 electron volts. Anyways, once we have these energy values, we can calculate what we call the electronic chemical potential, mu, the absolute chemical hardness by this formula, eta, and then the global electrophoretic index, which is this squared divided by 2 theta, and we end up with omega, the global electrophoretic index. And then we're going to put these all in the table. And we're going to compare it to bisulfide, and we're going to compare it to ethyl xanthate. We're going to just do the exact same thing. And when we do that, here's the first one. I've already forgotten what that was. Come back to here, the electronic chemical potential, and then the absolute chemical potential. And then I calculate the other term. That allows me to show you these, and then we can calculate the total energy based on all of this. And we can see that Orfom D8 is the most negative, followed by ethyl xanthate, which is, and then the NaSH is the lowest. Okay, and that's important, okay, because in order of reactivity, we expect this to be the highest, then this to be the next, and then this to have the lowest reactivity. So let's see how this bonds with, how Orfom D8 bonds with the chalcopyrite. So here's the chalcopyrite right here, and then here's the Orfom D8 reacting with that surface. So what we're showing is a monodentate structure. That's the assumption here. Okay. And then we're going to do that with pyrite. So here's the pyrite molecule, and here's Orfom D8 monodentate to the iron. And we try to do the same thing with molybdenite, and we can't get this bond to form. And that's because of molybdenite, we presume is because of molybdenite's natural hydrophobicity. So then, because we can calculate the energy for this combination of bonds, we can note that the chalcopyrite D8 bond will be slightly negative, 239, but pyrite is even more negative. What does that mean? Is that the pyrite will probably be better depressed than the chalcopyrite would. So if there's pyrite in the system, it's going to be depressed and report with the chalcopyrite. Okay, so interaction energies are the lowest for pyrite. Orfom D8 depresses chalcopyrite, but should depress the pyrite even better. And of course, once again, I'll repeat myself, results from molybdenite, we just could not attain them. Just wouldn't work. So let's go into the lab study then. Constraints here are our upper dosage is 1,200 grams per ton at pH 9. And we are, this is the optimal dosage, or I should say a minimum dosage. But what we did was we changed the Orfom D8 dosage. That minimum is somewhere in here. Anything less than that doesn't work very well. Anything greater than that seemed to work okay. It's hard to tell if it actually goes down and then goes back up, or if this is kind of if you average these numbers, and that's kind of an average for this dosage. Point being is that you need to be greater than that for this Orfom D8 to work. Note that the recovery up here in the red numbers are really accurate, are really good for molybdenite. So good recoveries, better grade at the higher dosages. You really don't need to go higher than that dosage. So let's take a look at the effect of pH, and we're going to keep the dosage constant now at 1,100 grams per ton. And you can see that in this case, we're getting really good moly grade, 39.3, 39.6, and 38.3, and it seems to work best at a moderate pH. You go too low, doesn't, it works, of course, there's nothing wrong with that, and it works at higher pH. But moderate pH is okay. And if you remember back at the zeta-potential studies, pH 8, 8.5, 9 seemed to work quite well. Okay, and again, look at those recoveries. Excellent recoveries for all the pHs. Okay, so the use of MLA, we're also able to follow boronite. Now, MLA is mineral liberation analysis. It's a technique that goes with the scanning electron microscope. So we follow these results. I'm just going to put all this up here. The boronite and the chalcopyrite gave similar results. The recovery max was 53.2. Now, this is in the first rougher float. And then as you increase the D8 dosage, the recovery went down a little bit. Now, mind you, we're not really high here. Then we put it up to 1,000, and then this came down even more. And if we were to go up around 1,300, I wish we had done those tests, but we didn't. We would see these numbers come down even more. Another point is that the recovery really doesn't change for the moly. So the chalcopyrite and the boronite start to get depressed, and we're able to follow the boronite because of the use of the MLA. Again, molybdenite was not effective, and the results are significant, and I can say that because we can plot our results based on the MLA, and we can model the recovery. And if we have a good model, this should be a 45-degree plot. And you can see that our experimental recovery versus the modeled recovery gives us a 1-to-1 ratio, a 45-degree plot. It's exactly what you want. So we can take those results and model them with the design of experiment studies. And now we can get three-dimensional plots that show you that, all right, from 8.5 to 10.5, if you're really low in dosage, it doesn't work very well. If you increase your dosage, you start to see a good effect, but it's this little cliff-like profile in here where you see the greatest effect. So you want to be at least greater than somewhere in here where you cite this bluish or this greenish color, somewhere in between. And once again, that's that 1100, 1200 D8 dosage range. And your desirability or recovery would increase substantially. This looks like it's up around 70% at a really high dosage at the lower pH. Okay. Again, the magic point somewhere around 1200. So the minimum dosage required, at least greater than 1000. Again, 1200 is probably good. Higher dosages just are not needed to maximize performance. And I can say that because these are rougher floats, and we also have 3 cleaner stages after that. So anywhere between 1250 and 2500 works. 1250, 1200, give or take, that's about where you want to be. pH range 7.5 to 10.5, but the effective range is 8.5 to 9.5. I'm going to skip this. Oh, I better not skip this. This is also important. This is another lab study. This is not a flow sheet, but we did a rougher float test, and a second one, and a third one, and a fourth one. We took the cons off of those two, mixed them together, did a first cleaner stage, and we took these two cons, combined them, and did a second cleaner stage. And then we took the concentrates from those and did a third cleaner stage. Then we reground that concentrate and did a second cleaner stage. We did a regrind on that concentrate, and we did a third cleaner step. So we're going to analyze the how well we did in this stage. We're going to analyze that product, that product, that product, and this product. And I'm going to compare those results. Okay, and we're doing that right here. So in the rougher float, the very first float, this is our moly grade, pretty good. Copper grade is starting to go down because it was at 25%. The moly head feed grade was 3.4. In the first cleaner stage, 43, then 50, then 53. So we go from 3.4, 25.6, 43.5, et cetera, et cetera. This is why you need 4 stages of flotation in the moly plant. Yes, sir. So 25% copper, 11, 3, 1.6, 1.2. Once you get to this level, you meet industrial standards. Ditto for the iron grade. And remember, this is copper iron sulfide. So if you're depressing the copper, you're also depressing the iron, even if pyrite is present. So in this case, optimum seems to be about 1250 grams per ton and around pH 7.5. The moly grade is definitely acceptable for industry, 53%. Okay, and I'm going to skip that. I'm going to go on to the plant trials now. I cannot tell you where these were done. Chevron Phillips will not allow me to say that. But I can show you that when you are using D8, now this is an industrial setting, that your average grade is around 80.5%, somewhere in there. And you compare that to NaSH, and it's probably 79%. And so the D8 is performing much better than the NaSH. Okay, now this is the moly recovery. So if you compare then the moly in the tail, you don't want the moly there, so this grade should be lower than the NaSH, and of course it is. So we're showing better performance there. In the case of copper, the copper in the moly concentrate is about the same between the two, and the copper in the rougher tail. Now this is where you want the copper to go. So this is about 27% copper in the copper con, and it's only 26.5% or something like that for the NaSH. Definitely performing better. And again, that's what you want. And you want to see a similar profile with the iron as you see with the copper. And in fact, that's what you're seeing. Okay, so equal or better than NaSH. In another study, this is the moly grade now that we're going to follow right here. They're using NaSH right here, and then they switch over to cyanide compounds, and you can see that the moly grade is a little bit better if they weren't not using NaSH but using cyanide instead. And then they're going to switch over to Orfom D8. Now there's a learning curve in here, and that's why they say this adjusting. And as soon as the operators get used to using this compound, you can see that the moly grade starts to improve just a little bit, but it's definitely better than NaSH and slightly better than the cyanide compounds. And if you look at the moly recovery, you're definitely better than the NaSH here. And you're kind of equal across the board with all of the other times or other chemicals. Okay, so in that case, you're definitely achieving moly grade and recovery, and you're performing better than NaSH. Okay, so in conclusion, flotation results showed Orfom D8 dosage around 12-15 needs to be exceeded. Your preferred pH range is 8.5 to 9.5. Rougher followed by 3 cleaner floats show the moly grade of 53% can be achieved, and that is equal to and it's also better than NaSH. Ditto for the copper, you can get it down to 1.2 in the moly con and the iron to 1.8%. Our goals here are 1.5 and 2 if I remember correctly. The mechanism, which is really what this presentation is about, is Orfom D8 chemisorbs on chalcopyrite, but not on moly. Cyclic voltammetry and X-ray photoelectron spectroscopy confirmed chemisorption because we were having electron transfer. And FTIR showed that the D8 bonded to the copper surface or to the chalcopyrite surface through the sulfur functionalities. But the xanthate did not desorb, and that is unlike NaSH. So favorable flotation results were obtained with Chevron Phillips at major copper moly companies. If anybody wants to know more about this, just contact Deb Laney at Chevron Phillips. The flotation test that we did in the lab, we used the SKT lab test results or lab test procedures. These were started by a gentleman named Peter Amalexin. Some of you may know him. He's with Minpro in Peru. He's now with Hud Bay in the States, also in Canada. And then we, of course, use DFT modeling, zeta-potentials, and adsorption densities to help confirm that reaction mechanism. So with that said, I would like to acknowledge and thank Montana Tech for the opportunity to work with Chevron Phillips, SME for acknowledging me with the Henry Crum Lecture Series. I am involved with your neighbor next door. This conference is now postponed to, I think it's March 23rd, 4th, and 5th. It's something like that. and I look forward to being live there. And hopefully many of you listening in will also be there, and I can get to shake your hand. This is the website for that conference. Again, it'll be in late May of 2022 now. I am helping Marcial Medina do that conference, and all these other gentlemen on there. And as of right now, that's what we have obtained so far. It will be a hybrid conference, but we hope most everybody shows up face to face. And these are the topics that are being pursued: minerals and reagents, machinery and equipment, analysis and control, and research and sustainability. And for Luis, he's seen this campus before. This is Montana Tech right here, looking across the valley from the M up on the hill. That would be Big Butte. This is Timber Butte, and these are the Highland Mountains in the background. Absolutely gorgeous. So thank you.
Thank you, Courtney, for this amazing presentation. And I hope that I can be there and shake your hand in person next year with Alfredo and all the other guys from the conference, and also with Professor Ianatos, our colleague from Chile. And we have some questions if you'd like to address them directly, or I can read those to you, or if people want to
go for it.
Open the mic.
I'm happy to answer.
Okay.
I love it.
Francioli, do you want to ask yourself? Please go ahead.
Okay, Francioli.
Okay, good evening, Mr. Courtney. I'm very curious about cyclic voltammetry. This is a common technique used to determine the chemicals or reagents interaction with minerals on ore.
Yes. Have you used that before? Or, people use a similar technique in studying corrosion of metals. And as long as your reagents are electrochemically active, in other words, they give up or accept electrons, then you can use cyclic voltammetry. And xanthate is one, particularly when it's ethyl xanthate, that's very electrochemical active.
Because I see FT is a technique very used to determine the adsorption, but I see that cyclic voltammetry is also used to corroborate results or something like that. Yes,
the results that I showed you, they were all done here at Montana Tech, and if you look in the literature, there is a lot of work on xanthate and copper, xanthate and galena, xanthate and chalcopyrite. Lots of mineral studies. And so we're very comfortable in knowing how that reacts. But what we're trying to do there is, number one, show that the D8 mimics that. And then number two, show that the xanthate does not desorb. It is just masked by the D8.
Great. And I have another question. If this is a common routine in your lab, make the molecular studies before to go to the bench flotation tests?
Say that again?
It's a common routine in your lab, make the molecular studies before go to the flotation tests.
Yeah, you know, I think one of those industrial tests was done before we studied this, and the second one was done after. So on the industrial wide, the answer would be yes. But Chevron approached us when they could not figure out a mechanism for this. And of course, we showed them through a long study that what we did, how it responds, and it's very similar to xanthate. When it comes to our lab tests, they were kind of side by side. We had to really think hard about the chemistry of the Orfom D8. And of course, as soon as I saw that, I said, this looks a lot like xanthate. And so I'm pretty sure that it's going to behave like xanthate. So we decided to go into the lab first and see if it would respond with the cyclic voltammetry. And sure enough, it did. So it's because of prior knowledge that we were in the lab first, or in the doing cyclic voltammetry rather than doing flotation tests. Again, only because of prior knowledge.
Okay, thanks so much, and congrats for your excellent presentation.
You're welcome, and thank you for the compliment.
Do you have more questions, please? Courtney, I think I'm going to address a question to you also. People can think about their questions in the meantime. So how about the differentiation between chalcopyrite and pyrite? Do you think it would be possible to try to do something like that in order to have a selective flotation between these two?
Yeah, I think there you need to be very careful with pH. Because I think a higher pH you can depress the pyrite. So yes, you could do that. You need to be careful with how much xanthate you're adding at that time. So I'm not saying starve it with xanthate, but I'm saying that with the right dosage of xanthate, the chalcopyrite will respond. So will the pyrite, but then the pH can be a good depressant, and perhaps a little bit of xanthate might help. And it'll help knock out that. I mean, a little bit of cyanide. I'm sorry, a little bit of cyanide will help knock out that pyrite.
Thank you very much for that.
You got it.
I think Petrus would like very much to know more about this DFT that you use, because he is also using DFT here in Brazil. So if you can talk a little bit more about that, we'd appreciate very much.
Sure, pick on my weakness. Yeah, you know, it's a powerful tool. And I presume you're talking as soon as I get through the, because we're coming up on it here. DFT, for a metallurgist, if he's got a good background in chemistry, I really believe that DFT has complementary information that can be added. Now, I can go into a little bit further detail. With chalcopyrite, the iron, and particularly as we're showing it here, the copper is the surface. The iron and the sulfur are subsurface. Okay, and with pyrite, the iron's at the surface and the sulfur's subsurface. So if this were flipped around and the sulfur were at the surface, then you would expect that surface to be hydrophobic. So if you give this some slight oxidation, you can make these surfaces metal deficient. In that case, the sulfur moves to the surface, and you can actually get collectorless flotation. Right? But the sulfur is going to come to the surface then. In moly, no matter what you do, the molybdenum is below the surface. The surface is always sulfur. So you don't have to do anything, and it's naturally hydrophobic. You can make it more hydrophobic with diesel fuel and other organics like that. but diesel fuel obviously works the best, and it loves to absorb onto the moly and what have you. So we learned a lot from this DFT modeling. We presumed that it was a monodentate here and here, and we just tried to get that to work with the molybdenite, and we couldn't get that bond to theoretically form by the computer. It just wouldn't. And so we associate that with the molybdenite being naturally hydrophobic.
Great, thank you so much for the explanation. Courtney, we have a message from you, from Luis. He had to leave the meeting, and he posted before, of course, a very beautiful message for you. I'm going to try to translate it for you. First of all, he's greeting you from Rio de Janeiro, and he told us that was a pleasure and an honor to listen to you again, because according to him, you're a legend, not professionally, but also personally. Okay, so
Louise and I got along very, very well, and I appreciate all the students that we had for that given year. It was wonderful. I think a lot of them got to see snow for the first time and go sledding and things like that, and they enjoyed themselves. One Brazilian student that we had, it was too cold. So I think she went home or went to another school, actually. That was a little warmer. I think she went to Tennessee, actually. University of Tennessee.
Yeah, depends whether you're in Brazil. If you reach something like -2 or 3, for them it would be like global extinction. They can't survive it.
Yeah, this morning we were probably -5, and here we are still in September. It was brisk, but the wind wasn't blowing, so it was all right. But we do get to -40 every now and then, and that's kind of bone chilling.
Yeah.
Don't let that stop you from coming here. Just come here in the summer. Don't worry about the winter.
Actually, I faced -27 in Germany. I was with Daniel Goldman, so you know him now. And definitely -40 is not going to stop me. You can count on that, okay? Don't worry.
Yeah. Tell Louise thanks, and it's always good to hear from him. And it was a pleasure seeing that when you posted on LinkedIn, he saw it and said, "I'm coming." So that was great.
Okay, thank you. Guys, do you have any other question? Otherwise, we're gonna say goodbye to Courtney. But if you have any questions, please address them now. Okay, thank you.
I am happy to stay here for another hour if you want. And don't be shy.
Guys, if you want to ask in Portuguese, please just do it, and I can try to translate your questions to Courtney also, okay?
There's Carla. She's being quiet. I'll butcher her name. Canuel? Yuri? Eduardo? Claudio?
Yeah. I just want to say some words, because a few months ago I contacted Professor Courtney, and I thank you very much, because the work he has developed are articles or papers that we can see the complete way to make the study, and it is very easy to reproduce what he writes in his papers, and what is quite a bit difficult in some papers about her, for example.
And thank you for those kind words too. My comment would be, a long time ago, I felt like my weakness was my writing. But because I concentrate on my writing, and I will go over something over it and over it and over it again before I'll submit it. It's actually my strength, and I recognize that because I put a lot of effort into it. But my goal is for everybody to be able to pick it up and understand what I'm doing and trying to say. Even if you're a 40-year professional in this area, my goal is to never be misunderstood. I always want to be understood. And I think that's an important thing for everybody. Not everybody's that way. Time is very important for them, so they rush through and they submit it. I don't do that, and I will never do that. If I won't say that. I have done that before. And here's this is honest. This is a comment that I got probably 4 years ago. Oh, Courtney Young submitted this paper for publication. I will be honored to be a reviewer for that paper. And then he reviews the paper, and his comments back were, I was very disappointed in this paper because it looked like Courtney Young did not really edit it. And guess what? I let the student take the lead, and I really didn't edit it. So I slipped up there, and I learned my lesson. I'm 55 years old at the time, you know, and I learned my lesson. If your name is on the paper, you need to take ownership of that paper. And so that's never going to happen again.
That's a very good advice, Courtney. Thank you so much for that. I was kind of worried that Francioli wasn't going to mention this because I have to thank you also for that. We're using a lot of your papers in our research over here about rare earth elements. As you know, we're using char and also combining it with other collectors, again, as you suggested. And the best result that we got so far was using 2 collectors, as again you mentioned. So
there you go. Yeah, that I was asked to write a paper on that for a chapter in a book. I did submit it. I can make that quietly available to you. It is a chapter in a book, and so you can't reference it until the book is out. Theoretically, you should purchase the book, but I'll make that available to you. I just submitted it a week ago, and the final version of that. This guy is pleased with the results, so I will send that. But thank you, I appreciate that.
I thank you, and I promise that I can do both things. We can wait, and then we can quote the book and also cite the book and also buy the book. Okay, as soon as it got out.
Yeah, I'm not the organizer. I'm just wrote a chapter, but it's going to be one of many that everybody jumped on because it's rare earths.
Okay. Now I'm also curious about this book. Definitely, I want to buy it.
Yeah. All right. I will let you know I'll send it to you.
That's great. It's gonna come out from SME also.
No. This one is it's like Springer catalog or something. It's an actual. It's kind of a journal, but it's a book. So I don't know what chapter I am in there, what have you. But it was such a pleasure hitting the send button and said, I'm glad that's done. Now there, as you know, Andre, faculty are under the pressure to publish. And I don't like that. I think it's wrong because too much gets published and pertinent gets lost. And by that, I mean, all right, my first publication, it covers this area. I'm going to come over here on the screen. It covers this much area. And then I'll follow up with that, and that covers this much area. And there's so much overlap. And then it covers this much area. And by the time I publish my 4th paper, I finally am into something totally different than the first paper. There's the 2nd and 3rd paper don't mean anything. And I try to avoid that. The other thing that I like to do is just get involved in something else. So I get involved in rare earth flotation. I'll be doing copper moly stuff. I'll turn around and I'll do uranium leaching. And I just love going after industries saying, hey, I'm bored. I need something to do different. You know? So it's not quite like that, but it's close enough.
I can imagine that you like new challenge, right?
I do absolutely love it. Yep.
That's great. So guys, we have time for one extra question. Okay, so please make your questions or you're gonna lose the chance.
You guys know how to contact me. My email, Montana Tech, it's cyong@mtech.edu. I'm normally very good at responding to email, but if I don't respond, it's because I didn't see it and it went to clutter or junk mail. So keep sending it to me until I see it. And worst case scenario, not worst, give me a call. I'm happy to answer your phone.
Okay, Courtney, thank you again so much for being here with us, to dedicate your time to Brazil. And as I invited you before, it would be our pleasure and our honor to host you here. Okay, so include Catalan also in your tour when you come with your wife to Rio de Janeiro. Let's go.
Yeah,
in country, okay?
Yeah, when we're in Peru, the goal is to cross the border.
Definitely. You're going to find us like Texas, okay? We're like in the middle of the country, quite hot in here, and you're going to see people using hats like Texas, but it's going to be a different experience for you here in Brazil. I think you're going to like it.
Yeah, that sounds great, my friend. Sounds great.
Okay, so again, thank you all for being here and to share this moment with Courtney with us. Courtney, you're also invited to come back as many times you like, okay? And hope to see you soon.
Sounds great, my friend. All right, you guys have a good night. It must be 8:30 there.
Definitely.
And thank you for your patience and letting me, or until I logged on. But it was wonderful. Thank you.
Thank you. Have a nice night. Bye-bye.
All right, bye-bye.